In this video, we'll be talking about the squeeze theorem for sequences. So the first thing we're going to begin with is such that we have a sub n, b sub n, and c sub n. Three different sequences. And let's argue then that we know that a sub n is less than or equal to b sub n, which is less than or equal to c sub n. So this is for all values of n. Okay, specifically greater than or equal to 1, doesn't really matter. It's really just any value of n. If I plug in n for a, b, and c, I can identify that they are patterned in this way. So for all values of n, a sub n is less than b sub n. For all values of b sub n is less than c sub n. What this might appear as is something like this, such that I have a bunch of dots here. This is c sub n. I have a bunch of dots here. This is a sub n, and then therefore b sub n has to be bounded between these two. Now I can do all sorts of things in the middle, but I know that it's stuck between those two for all values of n, meaning that this thing's not going to cycle up here above c for any value. Now, with that being said, let's also then state, it's important to note that what if the limit as n goes to infinity of a sub n equals to some value L, and the limit as n goes to infinity for c sub n goes to some value L, meaning they're the same value, not a different value. So that means that in this sequence here, c sub n, instead of approaching it by dots up, doing things up here, it eventually approaches to the same number as a. So the idea is that b doing all crazy things in the middle, but it being bounded between those two, also then has to approach that value, so that they're all approaching the exact same number. So again, the idea is the limit as n goes to infinity of a sub n is less than or equal to the limit as n goes to infinity of b sub n is less than or equal to the limit as n goes to infinity of c sub n. What we're trying to say here is that if I can prove the sequences appear like this, then I can follow up with proving that the limit of a sub n goes to L and the limit of c sub n goes to L as well. Then this statement is true such that this has to be L, this has to be L, and therefore the limit as n goes to infinity of b sub n is between either L or L, and therefore it has to be L. So the example we're going to look at for this is a sub n, I'll use a sub n, that's fine, cosine of n divided by n squared plus 1. So, just like when we did the squeeze theorem in Calculus 1, we're doing the squeeze theorem in Calculus 2, but this time we're just doing it on sequences, not functions. The rules don't change, though, because most sequences can be treated like functions. So what I'm going to do is I'm going to start with the fact that the cosine of n for all values is bounded between -1 and 1. I know this to be a true statement from my basic algebra and trigonometric rules. The next detail is that I can take this inequality and I can divide every single one of these pieces by n squared plus 1. Hence, I now have a pattern of this is less than this is less than this. If I were to take the limit of all three of these pieces, such that as n goes to infinity, this piece here, as n goes to infinity, well, wouldn't this thing then just be the bottom is infinity? So -1 over infinity, wouldn't that just go to 0? The same argument can be said for this one. Wouldn't that just go to 0? And therefore, the limit as n goes to infinity of the cosine of n divided by n squared plus 1 has to be bounded between 0 and 0, and therefore by the squeeze theorem of sequences, the cosine of n divided by n squared plus 1 will be equal to 0.